Okay, so today, just a brief introduction about myself. I realized I didn't put an intro slide. So my name is Noel. I'm from RisingWave Labs, and I used to be a NUS Hackers alumni. Now it's what? I think maybe 3-4 years ago. Yeah. So yeah, it's good to be back. I think this is my first Friday Hacks in a long time. And yeah, I hope everyone would enjoy my talk. So for me, I work at RisingWave Labs. I focus mainly on the kernel itself. So working on things like backfilling, observability, performance optimizations, and so on. Yeah, so if you all have any questions after the talk, you can also chat with me. Okay, so to start off, I think most people will be quite familiar with like batch systems. So let's say like Postgres, ClickHouse. Okay, I'll just wait for everybody to. Okay. Yeah, so let's say like Postgres, ClickHouse, like all of these different batch systems, right? Like both OLTP and OLAP. I think most people are familiar with this. So like over here, you can see we have like a simple console query, and that's a query that you run like ad hoc, right? And so this is known as an ad hoc batch query, right? So you can see the data is coming in, it's being ingested into these database tables, and then we just run a query over these tables. So then the question comes is like, what if you can process the data like earlier instead, like where the data is being ingested, right? Because if you process it like afterwards, right, when you run the query itself, first you get some query latency, right? Like you can see here, if the table is really large, your count start might take a while, right? And then, yeah, so that's one thing. And the other thing is in terms of freshness as well. Like once the data comes in, you also have to wait a while for the query to process it and to get the results. So freshness is also impacted. Yeah. So the idea is that whether we can process it earlier ahead of time, right? So one way to do this is in RisingWave, we use something called like materialized views. So that basically processes the data as soon as it comes in. So like when a record comes in, we actually have like a graph that updates like the state of, where we update the state of this query. For example, here you can see we have a select const from T, right? So actually this is represented as a graph of nodes, which you will see later, yeah. And so the idea is that now you can push the computation earlier, and you can process it then, yeah. So the way we do this is through incremental computation. Okay, so let's take a step back and see what we actually do in ad hoc computation. So here you can see like the computation is done like this is just normal SQL, right? So you create a table, you insert some data into the table, and then you select sum of V1 from the table T, right? So you do the computation right at the very end, right? And let's say TF has 1 billion rows. So then sum here will actually sum up all 1 billion rows when this query is executed. So this is done ad hoc, right? And so you can see here, right, like what if we shifted it earlier, right? So you can see the order of insert and the select is swapped. And we use something, this is just syntax, right? Just like we create a materialized view, which basically says that this thing is continually running and processing the results. And so rather than computing after the data is ingested, we construct a streaming job first, so we can incrementally compute the results. Yeah. So to compute sum incrementally, we actually need state, right? So we can state like the initial sum. The state of the initial sum is like 0. So at the start, let's say the table is empty, right? You can just say the sum, the current sum of this, when you run this query, right, it's just going to be 0, right? And then as we insert records in, you can see, for example, if we inserted like 100, 1,000, then we can just simply add them to the current sum. So let's say the sum is 0, right? So we just add 100, add 1,000, right? So as like the billion records slowly stream in, right? Then we just keep updating the state, just keep adding to the state, whatever the record's V1 column is, right? We just add to the state. So that way it's done incrementally. You don't have to ingest the data first and then run the query. So the compute is actually amortized. Like as soon as records come in, we actually update the state of the aggregation. Yeah. So this means, yeah, all you need to do now is to just, let's say you want to know like the aggregation, right? You want to know the results, right? Instead of running like the select count star on your table itself, you can just query this materialized view, just like select star from this materialized view M1, and then you get the results immediately. So you basically get freshness, better freshness, better latency, and like your compute cost, your compute graph will just look like smoother rather than like a burst when you're running the query. Okay. So just like a brief overview of like the stream query lifecycle as well as where we are going to focus. So generally, when a query comes in, because we are like Postgres compatible, right? So maybe the user is just using PSQL to connect to us, and then like it will go through these phases. So the initial phases are pretty standard, I guess, for like any database or compiler. So you go through the parser, the binder, the optimizer, and then maybe you hit the fragmenter, which will basically split it up into fragments that we can execute. I won't go too much. That's not the focus of today's talk, so I won't go too much into that. And then like the meta node there is just going to help to schedule the job. Yeah, so you will basically create the execution nodes that I talked about earlier. And I will go through that later as well. And then we'll start backfilling. So the idea of backfilling is that you created a materialized view over some tables, right? What if the table already has data, right? So you need to actually catch up to these tables. So that's the idea of backfilling. And then finally, once it has caught up, you actually start streaming like any updates coming in from these tables. So we'll focus on the streaming part first, because that's the core of it, right? RisingWave is a streaming database. So we'll ignore everything else at the start. So at the core of the stream engine, right, actually it's pretty simple. Like the core of it is just operators, right? And the idea is that these operators can form a graph, a DAG, right? So actually every stream job, right, like table, index, MV, sync source, all of these different relations, all of them just get like converted to DAG of like operators. Yeah, so we don't support, I know like SQL has like recursive queries and stuff like that. We don't support that, so that's why it's just a DAG for those who are wondering, yeah. And yeah, so I'm actually going to go over some concrete queries now to actually show you what kind of operators they are, right? Because this is still quite abstract. It's like, okay, operators, what is these operators? Right, so I'm going to show you how it actually maps over. So if you look at these two queries, right? So you have a table T here, and then now you have another materialized view. And this materialized view, all it does is that it selects values from T, which are greater than 0, and then you add 1 to them. And that's it. So it's pretty straightforward. So if you run explain on the materialized view query, you actually get this query plan here. And I'm just going to simplify it and show it in like more diagram. So you can see here, the first thing that we do is that we scan records in from the table T. Then after that, we apply the filter. So that's V greater than 0. And yeah, so V greater than 0, and then, oops, sorry. I realized that doesn't have that definition. Okay, but so the filter is basically V1 greater than 0, and then the project there is basically just applying the +1 to V1. Yeah. And then finally is the materialized step. So they actually, because RisingWave is a streaming database, right? After everything is processed, we actually persist it. So you can serve your materialized views from RisingWave. So you can actually query RisingWave and like ask it for the results from M1. Yeah. So the final step is actually to persist the results. Yeah, so actually these are all operators. So you can see they form a graph, right? Although this one is like linear, later on you'll see another example with joins that shows you that slightly more complex graph. Yeah. So yeah, okay, so simple example that we are going to walk through. So let's say we insert into T values 0 and 1. Yeah, let me get some water to drink. Okay, so let's say we insert into T values 0 and 1. And first thing first, right, you hit the scan node. So the scan node actually propagate the updates. So notice here, right, it's T going to M1, right? So M1 is actually scanning from T, right? So these changes actually are propagated from the upstream table. So you propagate over to the materialized view. The materialized view scan node, that's the input, right? You'll get 0, 1 as inserts. So you can see the op there is plus insert. Then that will get propagated to filter. Filter will remove values which are less than or equal to 0, right? So you're left with 1. And then we add 1 to the result, materialize it. So we'll store it. So now your materialized state inside there's 2, right? So that's like just for insert. And then let's say if we delete, then we'll have we'll delete the 2 rows from T. So these 2 rows are present in T, right? You'll still emit the change. So you'll remove 0 and then remove 1. You'll go through the filter again. So only only this one needs to be updated. Yeah. And finally, we will have nothing in the state because we deleted everything. So yeah, you'll propagate as expected. Yeah, so this should be pretty straightforward. Yeah, any questions so far? If not, I will continue on to other examples like aggregates and joins. No questions? Okay, great. So let's continue. So for aggregates, right, this is actually a stateful operator. So remember earlier where I went through the example of count, right? You actually need to persist some state inside so that we can update it incrementally. So same concept applies here, right? Like for count, you actually have to keep track of the current count. And then just add 2 because there are 2 records going in. Yeah, so after that, okay, I guess I missed this slide. But yeah, basically after that, you will remove 0 and then you will insert back 2, right? So the state of materialized now should actually be 2. Yeah. So yeah, you just propagate as per that. And that's how it works for stateful operators. So something slightly more complex now, this is joins. So for this join, it's just on 2 tables, T1 and T and T2. And we basically just select everything after the join. So yeah. So first thing first, on the left-hand side, for T, we insert these 2 records. It gets propagated. We initialize the state on the left-hand side. And then we need to do a lookup on the right-hand side. So whenever records come in, you need to check the other side to see if there's any matches, right? And if there's a match, then you need to output it. So no matches, no need to output. And then let's consider the other side now. So yeah, stream in some records, update the state. Okay, we check. Hey, there's a match on V1, right? So in this case, we will construct an output. And yeah, we'll basically persist this over to materialize as well. And yeah, we'll update the state. So for hash join, this is generally how it works in a streaming fashion. Yeah. Yeah, so you can see this actually forms like a more complex graph rather than a linear graph. So if you have multiple joins in your query, right, it can actually get more complex. Yeah. So there are actually different kinds of joins besides hash join. You can always look up our docs if you're curious. Yeah. So yeah, for stream operator bottlenecks, anyone want to take a guess? Like, what are the kind of common bottlenecks you'll see in streaming? Okay. Okay, I guess maybe. Yeah, but like in what way will you get bottlenecked? Like let's say if you need to do updates.
Because like your aggregate is being used even when we never meet the query.
Sorry, not too sure here I follow, but okay, good attempt. Okay. Anybody else want to try? Okay, if not. Okay, I think this is just from production. This is just basically I/O. I think usually I/O is the main bottleneck. Like reading from object store like S3 can take a long time. And yeah, we basically need like good concurrency patterns to avoid being blocked by I/O. And we need to have good data access patterns. So we can hit like cache, right? So you don't have to go and access I/O. So yeah, so here's the first example, right? For operators. So let me just step back to this. Right, sorry, I need to go back all the way. Or can I go forwards? Okay. So, okay, right here, yeah. So earlier I talked about like this whole thing, right? So actually there's two main areas that we do optimizations. The first area is inside streaming itself, right? So that's inside the operators, which was what I was going to cover. And the other area is in the optimizer. So that's what we'll cover later. But for this part, it's just inside the operator itself first. Okay, so we are done with all the hash join. Yeah. So first thing first. So join. I think join is a common bottleneck, especially like let's say I'm updating some dimension, right? So for dimensions, I'm not sure how many of you are familiar with dimensions, like dimension and fact table. Anybody raise your hand? Okay, I guess nobody's familiar. Okay, let me just give you a quick rundown of dimension table and fact table. So for fact tables, right, let me just give an example, right? So for example, like car sales, right? There's a lot of car sales. You have like maybe like your sale amount, you have your sale ID, and then you have like a car ID. So this car ID represents like what car you're selling, right? So that's like the column that you're going to join to the dimension table to widen your record and add more information to it. So your fact table itself has like all the car sales, right? And then you have another dimension table. The dimension table will contain car infos. So let's say what's the model of your car based on your car ID. What's the region in which this car was sold, stuff like that, right? So one dimension, let's say car models, right? You can imagine that for Toyotas, there can be like 1 million Toyotas being sold. So your car sales will have like 1 million of these records. So when it comes to joins, let's say a dimension is updated, right? The result is that a lot of the output of the join, let's say if it's a join between a fact and a dimension table, a lot of the updates of the join, a lot of the output records of the join need to be updated, right? So this can result in like cache misses, and then we'll need to refill the cache, right? So previously what we did is that we waited for cache refill to finish before processing the join. So obviously this is problematic, right? Yeah. So instead we refactor it to use Rust coroutines to use future stream. Sorry. So we use future stream instead. So when data gets fetched, continually streaming it in. Don't wait for everything to be fetched and buffered in our cache, right? And then process the data as it's yielded to perform join matching and to yield it downstream. So this avoids blocking on I/O. It also avoids OM issues due to buffering all rows in cache before performing the join matching. Yeah, so this is just one example of operator optimizations. There are more, like for example, like in aggregations, over window, things like that. These executor nodes can be quite expensive when they are downstream of a join. So other things that we do would be like compacting all the no-op operations, right? Like imagine you update and delete, but like you have a whole update and delete sequence, but they're all in the same key. So actually all of these can be compressed down to like a single insert or something like that. Yeah. So yeah. Okay, so that's focusing on the operator part. And then next you'll move on to optimizer, right? So for optimizer, it's actually part of our front end. So the front end will do like, different tricks to optimize the query so that when you generate the query plan itself, right? Like you saw the DAG of the operators, we try to find a DAG that's as inexpensive to execute, right, as possible for our optimizer. So just a question, like we use heuristic rules rather than cost-based optimizations. So anybody want to like, okay, you guys can just take a while to think about this. Yeah. If you can puzzle it out on your own, that's all right. Yeah. So this is just, again, batch versus streaming. So for this, It's actually because it's actually because to the database itself, right? Your workload is largely unknown ahead of time. It's not like a batch system where you actually have tables that you can analyze, like before you run your select query or whatever, right? You can run analyze on it to give like the database metrics to know how to come up with the best query plan. Can't really do this for streaming queries because you create them and then the data comes in, right? It's the other way around. So for this, we use heuristics. And we basically have like standard stuff. So like sub-query unnesting, sub-plan sharing, and we also have streaming specific things. So like we'll have this rule called separate consecutive join rule, right? So yeah, we were at the optimization, optimizer rule-based passes, right? So sub-query unnesting. So let's go over that first. So in this example here, you can see like the specific join here, right? It references the outer students table, right? So you can see the where clause, inside there's a subquery, right? And then inside the where clause of that where clauses subquery, you can see like s.classID that references students, right? So when you have this kind of correlation, right, like the dumbest way to execute it would just be like for each student, execute this where clause, right? But you can see like that's freaking expensive. So because you have to execute a whole subquery for each student inside this students table, right? So we want to find a way to like unnest this. So for this case, right, we can actually transform this. So inside RisingWave, this operator of like applying it to every single row in the table is called logical apply. So we basically can have like an optimization rule to transform logical apply to a join. Yeah. So instead of having to run the subquery every time, you just basically scan the tables, join them together, and then do some add a filter after that for the where clause. Yeah. So actually, if you look at our optimizer rules, like if you are interested, you can always take a look at it. So we have like a large chunk of them just for subquery unnesting. Yeah. So for streaming, it's especially expensive. In batch, it's also expensive, but streaming is even worse. So we want to like avoid it. Yeah. So yeah, this is we have a lot of rules for this. Yeah. And then for the other rule is that's specific to streaming. So we have something known as separate consecutive join rule. So you look at this query here, right? Like you have 4 tables, and then you just join them all on the first table's V1 column. So if you look at the query plan, we can just focus on the hash join, the 3 hash joins, right? So there's 3 joins, so all of them get transformed to hash joins. So the problem is that there is no pipelining. You see all of these are directly linked to each other. And because of our execution model, it's like we have to wait for like one poll on the actors in order for there to be any progress forward, right? So if one join is slow, the rest have to wait for it. So we basically introduce buffering via stream exchange. So you can see the stream exchange nodes. They also serve as buffers. And yeah, basically that would help to do pipelining and avoid being blocked on specific joins. Yeah. So that's for an overview of the optimizer. And then we also have backfill. So backfill also, we can split it up into 2 parts. One is within the operator itself, how we optimize it, and the other one is also in the optimizer, what kind of patterns we can use. All right, so for the backfilling optimizations in the operator, I think probably one of the most important ones would be prefetching. So we basically, when we scan from the table that we are backfilling from, it's ordered by the storage primary key. And because it's always ordered, when we fetch data from object storage, we can make sure to fetch adjacent data so that whenever we fetch subsequently, it's already stored in the block cache. So the block cache, okay, so RisingWave actually has tiered storage, right? So you have like cache layers, and then finally you have the object storage. So block cache is like just you have block cache, and then you have disk cache, and then you have object storage. So block cache is like an in-memory cache lying on the compute nodes. Yeah, so if you cache in there, your access will be directly from memory, so it also will be faster, right? So yeah, the example is shown here. So let's say you scan from this record, right? And it's ordered by key, right? So 124. It's not cached. So we fetch. And we also make sure to prefetch the other two, the foot 2 and 4, the adjacent rows basically, right? So we will hit the cache. And then the subsequent scans will also hit our cache, right? So yeah, it'll be fast. Okay. So next, on the optimizer side of things. So this is again, just now what I just covered was focusing on the operator, right? How we can make the operator faster, yeah. So in the optimizer itself, like basically backfilling has the same problems as streaming. You know, it's always blocked by I/O. So there's two ways we can improve like backfilling speeds, right? First would be backfill ordering. So like we basically want to reduce lookup size from joins, right? I think that's probably the most costly part of backfilling. If you are backfilling like a materialized view that has like several joins inside, yeah. And the other thing we want to do is we want to use indexes to cluster the data so that when we are like backfilling aggregates over window, things like that, we'll have better locality for the operator. So yeah, like let's just talk about the second one first. So that's index selection. So for that, it's like stateful streaming operators, you know, they have state. They need to read state in order to update it, right? Like they need to read, like, let's say you are doing aggregations, right? You need to read the previous state, and then you need to be able to update the state. So if the state is really large, right, you want to ensure that data access follows like a localized pattern, so that when we're fetching, you know, similar to the prefetch example just now, right, you're actually getting like adjacent data. Yeah. So this is important for what I mentioned earlier, aggregations over window, and like it's quite specific to the operators itself. So let's say for over window, it'll be like partition key. For aggregations, it'll be like the group key. And then all the data corresponding to that key, if we have the data ordered by it, it will be likely in cache, right? So yeah, so when we declare indexes, we declare it over like partition key, group key, so that the data is ordered for good locality and backfilling performance. Yeah. So that's for index selection. And then finally for backfill order control, you know, when we have backfilling patterns like this, let's say you create a materialized view with some aggregates, followed by a join on a fact table joining on a dimension table. Like we can have the scenario where, you know, one dimension entry matches like millions of fact side rows, right? So imagine like, let's say you update the car ID of Toyotas, right? And then you have like a fact table which contains all the car sales, right? If 1 million Toyotas were sold, then we have to update all the 1 million records in the output of the join. So this can be really expensive, right? And then let's say you have something downstream of the join, right? All of those things that are downstream all need to process that 1 million rows, right? This is going to take a long time. So yeah, you basically want to avoid this, right? Instead, we do the dimension table first, and then we do the fact table. So fact table, looking up the dimension table, that's really fast, right? Your dimension table is smaller. You match like less records, right? Because it's just matching a dimension, right? So yeah, like most fact tables will likely just like match a single dimension record, right? So this would be like much faster, right? Yeah, so I think that's it. Yeah, so those are the different optimizations that we do in the operator level, as well as in the optimizer in order to make streaming and backfilling performance better. Yeah, so any questions? Questions? No questions? Okay, if you guys are shy to ask, you can always come up to me and ask me later. Yeah. Okay, got a question from the back. Go ahead. Oh, it's not, okay, so database kernel, right, is different from like Linux kernel. Yeah, database kernel is different concept, yeah. It just refers to like the core of the system, right? Like, yeah, like a cloud database, like there's not all the infrastructure, but you have like the core database itself. Yeah. Any other questions? Okay, if not, we are done. You all can come and ask me your questions later. Okay, thanks guys.